This week, we will cover continuity, intermediate value theorem, and asymptotes of the graph. This is week 2, and these are the listed topics in the syllabus for week 2. Let's start with continuity. So in this example, by looking at the graphs, we will decide whether the given function is continuous or not over the given interval. Okay, let's look at the interval first. We will be dealing with the interval from -1 to 3. And let's start with the first graph. Okay, here is our interval from -1 to 3, right? The graph starts here, it goes like that. And then there is a hole here, it continues. Let's choose some arbitrary point, for example, 1. How do we check continuity at some particular point of a function? Maybe we can put a very quick recall here about how we check continuity for the graphs, for the functions. Okay. Can you mute yourself if you are not addressing a question for me? Okay, how to check continuity? At x equals a. Okay, this will be the summary of the corresponding lecture video, by the way. First, you will decide whether the function is defined. Maybe I should put here x. You will first decide whether f of x defined at x equal a or not. Second, you will check whether your function as x goes to a has a limit or not. This limit exists or not. It should exist, okay, to have a limit. Third, okay, you have limit exists, right? You have an existing limit. And you have an existing image. You already checked in the first item that whether your function defined at a or not. Your function should be defined at the point. Your function should have a limit at the given point a. And finally, you will check that whether they are equal or not. If these 3 conditions hold at the same time, then you can conclude that your function is continuous at the given point x equals a, okay? This is how you need to check the continuity. Let's look at the first graph again. Let's turn back to it. At this point 1, for example, is your function defined at the point 1? You see, there is a dotted point on the graph, so it is defined as this number, whatever it is. And then now I check the first item, second item. Does limit exist? From left, from right, if you follow the graph, you see that limit exists. Yes, because there is no jumps, there is no break at the graph, so one-sided limits will be equal. That's why limit exists here. And finally, the third item, the limiting value is the same as the defined value of your function, right? This is for sure. You can see it from the graph. So here at the point 1, limit of this function as x goes to 1 is the same as the defined value. This is the final item to check. That's why you conclude that f of x is continuous at x equals 1, for example. And this is the case for all the points on this graph except one point. This point, right? At x equals 2, f of 2 is not defined, as you can see. There is a hole. This point is not dotted. That's why, since the first item here is violated, it doesn't hold. You don't need to check the rest. You directly conclude that this function is not continuous at x equals 2, okay? Except 2, your function, there is no problem with your function, as you can draw the graph without lifting your hand. This means that your function is defined, limit exists, and limiting value is the same as the defined value of your function, except the point 2. Except 2, this function continues everywhere over this interval. Okay, let's check the second graph now. Starting from 1, I can draw the graph without lifting my hand till this point 3, right? From -1 to the end of the interval except x equals 3, there is no problem about the function. Always, you can check, for example, for this particular value. At x equals 2, your function is defined. Here is its definition. It is defined as 2. Limit exists. Limit of this function is also 2. Limit is the same as the defined value. So for the point 2, for example, they are the same. They are both defined as 2. So you conclude that f of x is continuous at x equals 2. But what about 3? At this point, is your function defined at 3? Yeah, it is defined this time. Let's say this is 3 over 2. Does limit exist as x goes to 3? Let's see. By the way, if you are checking for an endpoint of the interval, so this is the right endpoint of the interval, right? Then by looking at the second condition, you only check one-sided limits because it is the endpoint and there is no graph on the right side of it. We just check left-hand point. What is this limit? It seems like 1, right? I follow the graph and I see 1. And you see this is different than the value itself, right? This is different than the image. That's why this function is not continuous at x equals 3. Limit exists, image exists, but they are not the same. That's why it's not continuous. One more thing to emphasize, if you are at the right or left-hand point, you need to just check one-sided limit instead of the general overall limit. Okay, let's look at the next example. For this graph here, you see, I can draw its graph without lifting my hand. Everything is so perfect. Everything works really nice. There is no jumps, there is no breaks at this graph. That's why for all the values in this interval from -1 to 3, f of x is continuous for all of them. How do I know it? For example, let's check it 1. And it will be the same case for all the other points. For 1, it is defined as 1. Let's look at the limit from right and left. Limit exists and limiting value is also 1. For example, let's say limit of this function as x goes to 1 exists. Limit is 1. And look at the definition. Its image is also 1. That's why this function is continuous at x equals 1. And the situation is the same for all the points. Only one exception, at the endpoints, you need to check the one-sided limits instead of this overall limit, okay? Everything is so perfect for this graph. Let's look at this one, okay? What about the point 1? Is this function continuous at 1? Let's check it. First of all, let's try to understand the limit of that function. By the way, the given graph is defined at the point 1, right? F of 1 is defined as 0, obviously. Now, the first item is checked. Second, limit exists or not? Let's see. From left, from right, if you follow the graph, you see that right-hand side and left-hand side limit are not the same. That's why this limit does not exist. That's why you don't need to check the third item. You can directly conclude that this function is not continuous at 1. Is not continuous at x equals 1 because limit does not exist. Is that okay? Any questions? Reading the continuity from the graphs is so straightforward. You check these 3 items. If they are all satisfied, you conclude that your function is continuous at that given point. Any questions? Can I move on? Okay, let's move on. Second example is so similar. Here, our function f of x is defined piecewisely. Such definitions are called piecewise defined functions. For over different intervals, the definition of your function is changing. For example, from -1 to 0, your function is defined as x squared minus 1, which is this curve, okay? From 0 to 1, for example, it is defined as this line, which is this line here, and so on. This is the explicit definition, which is given as the piecewise defined function, and this is the graph of it. Now, we can check the continuity of this function for different points. For example, in part A, in question 5, all the conditions that I listed above, 3 conditions to check, are being checked here step by step. For example, at the point -1, is your function defined? Does the image exist? F of -1 defined as, you see, this is a dotted point, as 0. So it is defined. Next, as this is the endpoint, we can only check the left-hand side limit for that. Sorry, right-hand side limit for it. That's why we have this notation here. What about this limit? Limit of this function as x goes to -1 from right. What is that? Follow the graph. So the images are approaching to 0, right? Now, in the next step, we check that whether this limit is the same as the defined value. Yes, they are both 0. You can see that. This is also correct. Then, in conclusion, you can say that f of x is continuous at x equals -1, right? So because all the 3 conditions are checked, that's why your function is continuous. Next, let's look at the point 1. Now we are here. Is it defined? What is the image of 1 for this graph? What is the image of 1? Look at this point. This point tells you the image.
1.
It is 1. Okay. Does limit exist for 1? From left, from right. Okay. Left-hand side, right-hand side. Follow the graph, please. You see, left and right-hand side limits are the same, and they are approaching to the value 2, right? So the limit, if you look at the graph, you see that limit of this function as x approaches to 1 is 2, as you can see. Now, it is time to check whether the image is the same as the limiting value. No, you see, limit is 2, while the image is 1. They are not the same. That's why they are not the same. That's why f of x is or is not continuous at 1. Is not continuous at this point 1 because of this thing. Limit exists. Okay, image exists, but they are not the same. To have a continuous function, they should be the same. Is that okay? Let me move on if no questions. Is f defined at 2? This time we are at this point. You see, there is no definition for the point 2. It's a hole. It's an undotted point. That's why, okay, f of x is not defined at x equals 2. No need to check the remaining conditions. You directly conclude that this function is not continuous at x equals 2 because it is even not defined there. So this is a big no. It is not continuous. Okay, the rest, please exercise on them by yourself. These are exercise. Let me move on if no questions about this example. So I move on. Limits involving trigonometric functions. Okay, this time we don't have a graph. We just have the algebraic expression of the function, but we still want to analyze continuity. Okay, let's do this example. Sine x minus sine x as x goes to pi. How do you compute limits? Okay, our function is given with this definition. We want to check that whether f of x is continuous at x equals pi or not. We want to answer this question. How can we answer that? First of all, for this function, f of pi is defined or not, we will answer this, and then we will compute the limit, then we will check whether they are the same or not. Okay, so let's start with the limit. In computing limit for such algebraic expressions, you can start by inserting this limiting value here. Sine pi minus sine pi. What is sine pi? Okay, we can use unit circle to compute the values of trigonometric function. This is my unit circle. I measure pi angle. I end up with this point. And this point has this Cartesian coordinates, and always y component gives us the sign measure, right? Sine pi is 0. Then we have another sine pi, so the result of this limit is 0, which is the same as f of pi, right? Because this was the function, I directly insert pi to that function, so limiting value is the same as the image of that function, which means that this given function is in fact continuous at x equals pi, okay? So this is how you can check that algebraically. Any questions? Can I move on? Okay, let's move on. This is a past exam question from last year, I guess. I like showing past exam questions on problem solving sessions because students always tell me things like, Hocam, we are solving very basic questions in the problem solving sessions, but in the exams, questions are not that easy. You are right. Yes, I totally agree with you. But you just missed the aim of these problem solving sessions. By these problem solving lectures, I aim to give you a better understanding of the topic by showing you very basic fundamental examples. Without understanding the basics, you cannot understand the more difficult stuff, right? I cannot directly pass to past exam questions, for example. I need to show you some fundamental essential questions like that one. That's why we have to use our time here to understand the essentials of the content, the fundamental exercises. Only then, constructing upon them, you can understand more difficult, more professional examples like exam questions, of course. But I wish I have more time to do lectures with you to go over all that past exam questions, all that difficult questions, but the fact is that we don't have enough scheduled slots for that. For these problem solving sessions, I have to give you the basic understanding by solving the essential examples. So I think I made myself clear on this, but sometimes as time permits, I will show you also more interesting stuff from exam questions like this one. Okay, we are given a piecewise defined function again. We want to find the values of a and b such that makes this function continuous at the point 2. First of all, let's try to understand this function, how it behaves on the left and on the right side at x equals 2, okay? So on the left, over here, our function is defined as, you can see for x less than 2, it is defined as this. For x is greater than 2, the function is defined as minus cx squared plus a. And we want to find the values of b and c, and b is the image of this function at x equals 2. We want to find the values of b and c that makes this function continuous at 2. So we need to check continuity at x equals 2. How do you check that? You look at the limit of your function, right? To understand the limit, I think we need to look at right and left-hand side limit of the given function. Okay, like this. As x goes to 2 from left, from right. Now we are trying to understand the limit. Why? Your function is already defined as b there. So first condition is checked. Your function is defined. Now I am searching for the limit. On the left side, you see that your function is defined as x minus c, and on the right of 2, on the right of the point 2, your function is defined as c squared minus c squared plus a. Okay, then start computing the limit. X goes to 2, that's why I insert 2 for x. 2 minus c on left, on the right we obtain minus 4c plus 8, and this equation will give you the value of c as 2. Okay. If we want that limit exists, c has to be 2. Okay. If C is 2, what is the limit? Can you tell me that? If C is 2, what is the limit of this function as x goes to 2? You can just insert 2 here to compute the left-hand side limit or right-hand side limit. They will be the same. So just insert 2 here, limit is 0. And this should be the same as the defined value of your function to have a continuity there, right? So f of 2 is given as b, and this image should be the same as the limit. So from here, we see that b should be 0. So these are the values of b and c to make this function continuous at x equals 2. Is that okay? Okay, let's move on. Now, we have this one. This exercise is about intermediate value theorem, okay, which is covered already in the recorded lecture videos. You are supposed to watch it before coming to this class, right? So I assume that you already have an idea about intermediate value theorem, but still, I want to summarize it for you or remind it for you. Recall. I'm recalling intermediate value theorem here. For all the theorems in the universe, no matter whether it's a physics theorem or whether it's a mathematics theorem, all of them have a structure. All of them has some assumptions, and depending whether the assumptions being hold or not, they have a conclusion. So all the theorems should be an assumption part and a conclusion part. That's why now I will try to list the assumptions of intermediate value theorem for you. The strongest assumption of this theorem is the following: f of x should be continuous on a closed interval, okay? Next assumption, we want to have some information about the values of this function at the endpoints. For example, let's say f of a is negative at one of the endpoints and f of b takes a positive value. By the way, this is a particular case of intermediate value theorem, which we will use to solve this exercise. You will see a more general statement in your course book. I am just writing a particular case of it. Okay, these are the two assumptions. In fact, this is my assumption box, okay? If this holds and this holds, then, if the assumption box holds, then there will be a conclusion of this theorem. Now I will write the conclusion box. Conclusion is what? Then by intermediate value theorem, there is this assumption, this conclusion is given by this theorem. There is at least one number c inside this interval such that f of c is 0, okay? This is the conclusion of intermediate value theorem. Do you understand what does this theorem tries to tell us? If the image of a function is 0, you can call this point as the root of it or the 0 of that function. They all mean the same thing. So by using intermediate value theorem, you can prove that the given function has a root over a given interval, if, of course, the assumptions hold. Okay, I write the statement here in the most clear way I can, but still, I think this needs more clarification by illustrating it, right? Okay, this is the Cartesian coordinate. And let's look at the assumption. We assume that f of a is negative. Okay, let's choose a negative image for a. And we assume that f of b is positive. So I choose a positive image for b. Okay, so our function passes through these 2 points, f of a, which is negative, and f of b, which is positive. Now I will connect these 2 points with a continuous graph. You see? This is a very strong assumption, very useful assumption. If your function is continuous, it behaves very nice. It behaves perfectly. Because if it is continuous, it cannot have any breaks. It cannot have any jumps. It cannot have any holes on it. For example, I cannot just draw it like this, then jump to here. I cannot do that because it is continuous. Or I cannot just put a hole here and move on. No, this is not the case because I have to draw a continuous function. That's why starting from this point till this one, I will connect these 2 points with a continuous graph without lifting my hand like that. I cannot lift my hand to insert a break, to insert a jump, to insert a hole, because this function has to be continuous. That's why my function has to cross x-axis at some point between A and B. And this crossing point will be this point C. Why? Because what is the image of this point now? What is the image of C?
0.
0. You see, this crossing point is the point that is mentioned in intermediate value theorem. It says there is at least one C such that whose image is 0. See, this is the root. Why we are saying at least? Why we are using this word here? Because there may be more than one crossing point. So you see, I can do like this and still connect these 2 points together. And in that case, there will be more than one crossing point. There will be more than one root, right? That's why we need to say at least one crossing point there should be. But let me leave my graph in this form. Okay, just a second. Yeah, it worked. Let me leave it like that. There will be at least one C where we cross x-axis. And you understand that I use this very strong assumption continuity not to pass over x-axis. I cannot lift my hand, I cannot break the graph. That's why I have to cross x-axis like that. Is it okay? So this figure shows everything about intermediate value theorem. It is very nice to see the illustration of it to understand. Okay, let's solve our example now. 2 sin x equals x. We want to find at least 3 roots of this equation. To deal with such exercises, if you search for the roots, always you will use intermediate value theorem. And to be able to use it, you need to first check the assumptions continuity. That's why I am creating a function now from this equation. So my function will be 2 sin x minus x, okay? 2 sin x, just take x to the left side like that. This is my function now. Is it continuous? Sin x and cosine x, these 2 trigonometric functions are always continuous. They have no discontinuity points, as you can insert any real number x here for sin x. Sin x is always defined. X as a polynomial, also another everywhere continuous function. That's why altogether this is a continuous everywhere function. Okay, that's why I can now try to find some negative and some positive values of this function to conclude that there is at least one crossing point in between. So let's start searching for it. For example, let's try f of pi. Okay, why not? F of pi is 2 sin pi minus pi. Sin pi is 0. Remember how we use a unit circle? Sin pi is 0. So the result, the image here is minus pi, which is negative. You see, I find a negative image. By the way, this part is always up to you. You will try you will choose by yourself some points and try to find some negative, some positive images. Let's now try pi over 2. Why not? Sin pi over 2 minus pi. Sin pi over 2 is 0. That's why the image here is, sorry, sine pi over 2 is 1. The image is 2 minus pi. Oh, by the way, this is also pi over 2. Yeah, this image is positive. Then let me draw here what's happening with this function. I find the image of pi. It is somewhere here, negative, right? Somewhere here, minus pi is the image. Then I tried pi over 2. I find a positive image. 2 minus pi over 2 is the image of it. It is positive above x-axis. And then what can I conclude at this point is to connect these 2 points with a continuous graph like that, I have to cross x-axis, and this will be the first root of mine. Okay. Then by intermediate value theorem, there will be a crossing point. There will be a root, which I call as C1, such that f of C1 is 0. You see, this is the crossing point. But I need at least 3 roots. That's why I keep searching. Let's try f minus pi over 2. Why not? Then 2 times sine minus pi over 2, minus plus, right? Then this image is minus 2 plus pi over 2, which is exactly the negative of this image. So it is negative. Positive, negative. You see, it happens again. Now I am here. Let's say this is the point 0 minus pi over 2. It gets a negative image. Then to connect these 2 points, pi over 2 and the image of minus pi over 2 and the image of pi over 2, one of them is negative, one of them is positive, as you can see. I have to cross x-axis again. And I don't know whether it is 0 or not. And this root, I will call it as the second root, okay? F of C1 is already determined. Now I detect one more crossing point between these 2 positive and negative images. Again, by I with t, there is another crossing point, which is in fact the second root. And I need one other root. That's why I will try the image of minus pi. Just insert minus pi to your function. Minus plus pi. So this is pi. You see, positive. From negative to positive, I will connect. That's why I have to cross x-axis once more. So minus pi is somewhere here, and I obtain a positive image for it. It is somewhere here, positive image. Now I need to, from this negative image to this positive image, I need to draw a continuous graph like that. So you see, I have to cross again x-axis, and this will be the third root of this function. Okay, from between these 2 positive and negative images, again, there will be another crossing point where I call as a C3. It will be the third root. You see, by applying IVT 3 times, I proved that there are at least 3 roots, C1, C2, C3 of this function, where the images of function are all 0. That's why I call them as roots. So this is how you need to apply intermediate value theorem to detect the roots of your function. One thing is so important, so crucial. You shouldn't forget to check whether it's a continuous function or not. If it is not continuous, you cannot use intermediate value theorem. First of all, assumptions should hold. That's why always start by checking the continuity of your function. Otherwise, you cannot use intermediate value theorem. Is that okay? Can I move on?
Yeah, hocam, that's okay.
Okay. So let me check the time. Okay. We can look at this part 2 and then we can take the break, I guess. Limits involving infinity, asymptotes of graphs. Let's look at this part. You see, in this part, we will try to compute the limit of the given functions as x goes to plus or minus infinity. So let's start with 17. Okay. Limit as x goes to plus infinity, 7x cubed divided by x cubed minus 3x squared plus 6x. Okay. So normally, if you insert x goes to infinity to these polynomials, look at the denominator. It will get infinite value if I insert x equals infinite. Look at the denominator. If you have a polynomial, you will always just look at the dominating term. X cubed goes to infinity if x goes to infinity. So this rational function behaves like infinity over infinity. What is it? Is it 1? Can I simplify them? Obviously not. This is an indeterminate form, okay? Don't forget. 0 over 0, infinity over infinity, infinity minus infinity. These are all indeterminate forms. That's why we need to invent something here to get rid of this indeterminate form. Okay, we don't know the result of it yet. The result is hidden inside this indeterminate form. All we need to do is find out what it is by inventing some simplifications. How we can invent simplifications? If your function is in the form of polynomial divided by polynomial, you can always take highest degree term out from your polynomial. I mean, you can decompose it like this. Okay, so I can write the denominator like that. Only then you start having this simplification. And then you start seeing the result. As x goes to infinity, what do you think this term is? 3 over infinite. What is it? 3 over infinite.
0.
It is 0, obviously. 6 over infinite. It is 0. So what we have as a result here, we have just this coefficient and only 1 at the denominator, so the result is 7. If you have polynomial over polynomial and want to compute a limit as x goes to plus infinite or minus infinite, you will proceed like this. You will take the highest degree term out from your polynomials. Now, I will solve the same exercise as x goes to minus infinity to show you nothing will change, okay? It will exactly be the same. So we will do the same decomposition here. Okay, limit as x goes to minus infinity. This will again simplify 3 over minus infinite. What is it? Minus infinite, 3 over minus infinite. No matter whether it is plus or minus, you are dividing 3 with a very huge quantity. Again, 0. Again, 0, right? Nothing will change. So the result is again 7 over 1, 7. As x goes to infinite or minus infinite. Again, this behaves like infinity. This time it is minus infinite over minus infinity, as these are odd powers. And you can get rid of this indeterminate form by proceeding very similar to the previous case. Okay, if no questions, I want to continue with 19. Okay, let's see. What kind of behavior does this function have as x goes to plus infinity? Okay, so again, as x goes to plus infinity, numerator is too big, denominator is too big. It is an indeterminate form. How can I get rid of it? By inventing simplifications by taking the highest degree terms out from the polynomial like that. Then 1 over x, then 31 over x to the power 5 divided by x to the power 6. Simplify. You will have still x at the denominator. Be careful about that. 1 over infinite is 0. 31 over infinite is 0. So we end up with what? We end up with, as x goes to infinity, I have 10 here, and I have just x here, right? So what is the result? What do you think? 10 over infinite. What is this?
0.
Exactly. A number divided by infinite is 0. Okay. The result of this limit is 0. And finally, we can deal with 20. At the end, I will try to emphasize something on these three questions. We will start deriving some general rules. Let's first complete this one. As x goes to infinity. Just look at the dominating terms to understand the behavior of it. As x goes to infinity, it behaves like infinity over infinity, indeterminate form. You know what to do. You will take the highest degree terms out. 7 over x minus 2 over x cubed divided by x squared 1 over x. Like that. Okay. These are all going to 0 as x goes to infinity. Simplify, simplify, you left with x in the denominator. So as x goes to infinity, what do you have? You just have x, right? So what is this limit? Obviously infinite. Okay, now I want to take your attention on something. In the first example, the degrees of the polynomials were equal. So if you have polynomial over polynomial, if the degrees are equal, and also if you compute the limit as x goes to plus or minus infinity, you just take the ratio of the coefficients. This is the quick way of understanding the limit. Again, compare the degrees. If the degree of the denominator is bigger than the degree of the numerator, the result is supposed to be 0 because the denominator grows faster with a bigger degree. And again, compare the degrees. If the degree of the numerator is bigger, numerator will grow faster. That's why you are supposed to get an infinite as the result of the limit. Is that okay? So any questions about this example where we understand the quick way of computing limits as x goes to plus or minus infinity of rational functions consisting polynomial over polynomials? Okay, I think this is the exact time to take the break. I stop sharing my screen, stop